This next talk is from our Breaking Ground track. We have Indiana Moreau discussing Repo Jacking, how GitHub exposes over 70,000 projects to remote code injection.
Welcome to my talk on Repo Jacking and how GitHub usernames expose 70,000 open source projects to remote code injection. My name is Indiana, and today we're going to be talking about Repo Jacking, a novel supply chain vulnerability which is very widespread and results in remote code injection. We're going to start by talking about supply chain attacks in general and looking at some common instances, and then we're going to talk about Repo Jacking, how it's exploited, how we came about it, and just how widespread it is. We're going to look at all open source projects and how we managed to scan them for this vulnerability. And then we're going to look at the final impact and which kind of projects are impacted. And finally, we'll look at remediations and how to protect yourself from this vulnerability. So let's start by talking about supply chain attacks. There are two main types of supply chain attacks. We've got hardware supply chain attacks and software supply chain attacks. I'm going to be mainly talking about software supply chain attacks. And in this space, you have something called vendor supply chain attacks. And for example, SolarWinds made the news. And this is where an attacker targets a vendor to target downstream companies, essentially. But I don't want to talk about vendor supply chain attacks as much as I want to talk about open source supply chain attacks. So attacks that are targeting open source software. Obviously, open source software is super relevant nowadays. Virtually every application is using at least something of open source. And because of that, attackers are targeting it more and more. It's a very lucrative target for attackers because open source software is usually not as well funded or defended as something like a vendor. I think that leads on to one key difference between vendor and open source attacks. When you're going for a vendor supply chain attack, you want to go after the biggest and baddest vendor because they're the one that everyone's going to be using. But for open source projects, that's not necessarily the case. Here's an example of a page called Unseen Infrastructures, maintained by libraries.io. And what this page is basically looks at repositories and projects which are open source and are highly dependent on. So lots of different projects use them, but aren't very popular. So if we look at example number 2 here, Concat Map. What this is it is a project that has 800,000 dependent repositories. So lots of different projects that depend on it, but it only has 30 stars and 1 contributor on GitHub. So it's not very popular. This is a prime target for an attacker because it's not very known, it might not be very well defended, but it's very dependent upon. If you look, these are all different projects that use this concat map, and some of these are definitely large projects that I'm sure you all recognize. So that's why open source supply chain attacks can be more dangerous because even the small targets can be very impactful. Now for these small targets, like concat map, maybe it's a very small library and you can't find a vulnerability in it, or an attacker can't find a vulnerability. And so instead of having to directly exploit that library, sometimes they can just ask the owner if they can have it. This actually happened back in 2018 with the event stream library. This was a package very much like concat map that was loaded by thousands of different projects. Now, a malicious attacker contacted the owner and said, "Hi, I would like to push new updates and I want to update this library because I use it," trying to present themselves as someone who wants to help the development. The owner had moved on to different projects and said, "Sure," and passed on the event stream library. And almost immediately, that malicious attacker loaded in malicious code. And that malicious code was attempting to break into a cryptocurrency wallet that was using EventStream as a dependency. Now, eventually they were caught. And the scary part of the story, though, is that they were only caught because they used an outdated API call within their malicious code. So that popped up a warning every time the code was run. If they hadn't used that API call, who knows how long this could have gone undetected for. So this really highlights why open source supply chain attacks can be very valuable because you can target very small targets and have a very large impact. Now, let's say that you can't find a vulnerability and you don't want to ask for the project. One alternative to break into these projects would be repo jacking. So let's talk about how I actually ran into repo jacking. So the first time I ran into repo jacking, I was doing a code audit, a code review for a project. This project was written in Go, and it had a dependency to a GitHub URL. Very common, I've done it hundreds of times. Browsed that URL to see what it was, and I got redirected to a different URL, different GitHub repository. I thought that's very weird, I've never seen that before. Tried again, same thing. So I thought that was bizarre. And if we look at a GitHub URL, there's 3 main elements. You have the protocol and domain, that's the first part. That's not going to be changing, right? That's static. And then the second part is the username, and the last part, the repository name. The username is the one who determines the repository name, since the user gets to name the repositories. So essentially in this URL, the key identifying part is that username. So I had this URL, which was loading code and it was working, and I decided to go see what the user was. And when I tried to browse to the username, I got a 404 error, user not found. So that user doesn't exist, but this project is clearly loading code from a URL that points to it. So if that user doesn't exist, I thought, what happens if I were to re-register it? So I tried and it worked. So I could re-register this user, and I thought, what happens if I recreate the repository? So I tried that and it also worked. And now that URL, which used to redirect me to a completely different repository, stopped redirecting me and brought me directly to this repository, which I just written. And since the project I was looking at loaded in code from this as a dependency, I now had gotten remote code injection on that project. And that's the key premise basically of repo jacking. GitHub allows username reuse. And because of that, if someone is to rename or delete their GitHub username, then anyone can go in, re-register them, and any of the old links pointing towards that username are now hijacked and would result in code injection. So here's a couple of key points of repo jacking. It's conceptually similar to S3 bucket sniping or subdomain takeover, if you're familiar with those. Essentially, you have a location on an online service or a name or unique identifier that can be re-registered after it's deleted. It's very dangerous because since GitHub is a code hosting platform, a lot of people use it to load in dependencies. So it often results in code injection. And another scary part of repo jacking is that you may not change anything in your code. You might have all your repositories which you've checked and they're not redirecting, they're not doing anything funky, but all of a sudden one of those dependencies owners decides to change their username, and all of a sudden now you're exposed to remote code injection because of repo jacking. So it can happen to anyone without changing their code. And then obviously, since GitHub is public, this is exploitable by anyone, and it's trivial to do so. You just have to be able to create a GitHub account. Now let's look at 3 specific scenarios that can lead to repo jacking. So scenario number 1 is the most obvious. A user deletes their account. So if a user deletes their account, then obviously that account is going to be re-registerable by anyone. And in doing so, anyone who points to the old URLs are going to load in code from this new account. Now the issue with when a user deletes their account is that in between the time that a user deletes their account and a new account is re-registered, all the links are going to break. So all the dependencies are going to not work. So anyone who tries to update their project and is using one of these links is going to see an error and is going to change where they're pointing at. So for an attacker to exploit this scenario, they have to be very well timed and know exactly when a user is going to delete their account. Now, this scenario has actually happened in the wild before. Kodi, which is a video streaming platform, allows for add-ons, which can be loaded in from GitHub URLs. There's a popular add-on that was loaded in from a GitHub URL, but the owner of that repository deleted their account. In doing so, that add-on broke whenever it tried to update, but someone went back in and re-registered that account name. So now they could start pushing updates to all of these Kodi instances. Now in this case, it wasn't malicious, but if they wanted to, they could have pushed any type of update to all these instances and taken them over. So that has happened in the wild before, but effectively it's very noisy, right? Everyone is aware of it because everything starts breaking. Scenario 2 here, a user renames their account. I'm going to talk about scenario 2 and 3 because they're distinctly more dangerous than scenario 1. Scenario 2 over here is where a user, they rename their account, which means that now their account has a different name. And that makes sense, right? You can re-register that original name. And scenario 3 is a user transfers a repository to another user and then deletes their account. Now, scenario 2 and 3 are more dangerous because of something called repository redirects. So back in 2013, GitHub implemented a new feature called repository redirects. The premise was if someone renames or transfers a repository over, all of the old URLs will continue working. And this is exactly what I saw when I first found repo jacking. There was a repository redirect set up when a user renamed their account, which meant that all the old links were now pointing to the new links. So look at how that actually works. Right now, if you browse to github.com/twitter/bootstrap, you'll notice that you get redirected to twitter.com/twbs/bootstrap. And this is a repository redirect. Twitter used to have the Bootstrap project under its user, under its GitHub user, and everyone used to point to that link. And then when they transfer it to a different user to manage Bootstrap exclusively, then there was a repository redirect that was set up. So everyone who had that original, that top URL as a dependency, it would now get redirected to the bottom URL. So that's very useful because it doesn't break everyone's builds and everything continues working. Now the issue here is that if Twitter were to change their Twitter username to something else, then every link that used to be pointing to that Twitter/bootstrap would be hijackable, and everyone who depended on that URL would then be vulnerable to code injection. So that's the dangers of repository redirects, and that's the reason why scenario 2 and 3 are more dangerous because they set up repository redirect. So a user renames their account, GitHub sets up a repository redirect to redirect all your repositories to the new account, but that username, that original username, is still available to be re-registered. So anyone who depended on those projects as GitHub URLs, all their projects will continue working, their dependencies will continue updating fine, but now they might be vulnerable to repo jacking. And another interesting thing about repository redirects is that it works for Git clone operations. So someone doesn't have to change all their Git references every time they update their user or transfer repository. So that's essentially repo jacking. Very impactful, very easy. And so we went to GitHub. We said, all right, GitHub, this is what we found. We think this is very dangerous. And the response was, oh yeah, we know about this. And that's okay, because we've already mitigated it with this fix. So they pointed me to this fix. And essentially what they've done is they've said any project that has had more than 100 clones in the week leading up to it being renamed or deleted can no longer be re-registered. So they blocked re-registering for projects that had more than 100 clones in the week before. This is unfortunately not a sufficient fix in my opinion, because if you look at something like Microsoft/TypeScript, that's obviously a very big project, and that's going to have more than 100 clones for sure in the week leading up if it were to be renamed. But if you look at something like ConCatMap that just had 30 stars, one contributor, that's very unlikely to have 100 clones. So if that ConCatMap user were to rename their account, it would now be vulnerable to repo jacking, and it would be very impactful. We saw the types of projects which used ConCatMap. So this can work for very large projects, but unfortunately, very large projects are not necessarily the ones that would be targeted and would be the most impactful. So we know that repo jacking exists. GitHub's not going to change the way it works. So let's look at all open source projects, scan through all the code, and see how many projects are actually vulnerable. We're going to walk through the different steps we took to perform this mass analysis. So step one is data collection. We've had two data sets here. The first one is the GitHub activity data, published directly by GitHub. It is raw source code. 3 terabytes of raw source code. That's really great because you can search through it and extract all the GitHub links out there. The only issue is that was last updated in 2019, so some of the data might be stale. And the second data set is libraries.io. Libraries.io is the same page that maintained that unseen infrastructure page before. And what they do is they essentially maintain a database of dependencies between open source projects. This is really great because it's formatted data, and once we find all the vulnerable projects, we can use this to build out our graph database and find everything that depends on a vulnerable project. Those are two data sets. So we take these data sets, scan through them, takes quite a while, but we end up with just shy of 4 million unique GitHub links in source code. So what this means is these are links that are pointing to GitHub, and they're unique links pointing to GitHub in the source code. But we still need to clean this up. So step two is cleanup. We might have links, for example, like this. This is a README file, and there's a link to a GitHub repository, but obviously code is not going to be loaded from a README file. So this is not impactful, right? Even if someone were to take over this repository, they wouldn't be able to inject code or anything. So we want to remove that, and we want to remove, for example, GitHub URLs in a comment, which we see very often, because that obviously will not be loaded either. What we want to keep are things like this. This is a Docker file, and in here, they're doing a wget on a GitHub repository. So if this protocol buffer user were to change their username, then this wget would be vulnerable to repo jacking, and therefore the Docker file and the Docker container would be vulnerable to code injection. Now, another thing to note when we're cleaning this up is that different package managers have different way of referencing a GitHub URL. Most note here is the NPM and the RubyGems shorthand. So if you look at the top one here, you don't even have to include GitHub anywhere. If you just include a username / a repository as the dependency, NPM is going to assume you're talking about GitHub and go download that code. And I think that really speaks to just how common linking to GitHub for dependencies is, because they've got this shorthand where you don't even have to say it's GitHub. Everyone assumes, all right, if it's a repository username, you want it from GitHub. Clean this up, we want to make sure we get all the links for GitHub. And after that, we're left with 2.1 unique impactful GitHub links. So these are links which are going to be loading code directly from GitHub. So if any of the links are vulnerable to repo jacking, then that link would lead to code injection. So we've got all these links. Now we need to extract the usernames, right? We need to see which ones exist and which ones don't. which ones can we re-register. So we searched through 650,000 GitHub usernames. It took quite a while over the GitHub API with the rate limiting, but eventually we were left with 50,000 unregistered usernames, 7%. Now this is really a large number. When going into this, I was expecting maybe sub 1%, but 7% is quite significant. And this is the point where I kind of realized just how impactful this might be. So we've got 50,000 unregistered usernames, and now it's the easy backwards steps where you see, okay, got all these unregistered usernames, how many links are using those unregistered usernames? So we've got 92,000 hijackable GitHub links. So links that are used to load in code and can be hijacked by just creating a new username. All right, and how many projects are using one of those links? I ended up with 18,000 directly vulnerable projects. So these are projects that are directly vulnerable to repo jacking. Let's take a look at one example. Here we have Algorithm Search Helper version 3.2.2. It's since been fixed, and what we're seeing in the top here is a package.json file, and that is the npm package manager file that tells you where you want to pull in dependencies. We've got this shorthand, which you'll recall is links to the GitHub shorthand here, where it's a superwolf user / mailsmith in place repository. So first step to see if it's vulnerable, we check the user. Does this superwolf user exist? And we browse to that, and it does not. So this user doesn't exist, so it can be re-registered by anyone. Now, in that case, why would a Go Search Helper be using this as a dependency? If we actually browse to this URL, we see that it's getting redirected to mailsmith / mailsmith in place. So what probably happened is that superwolf user renamed their account to mailsmith, and it set up a repository redirect. So Algorithm Search Helper is still loading in code from here, but if we were to recreate that superwolf user and recreate that mailsmith in place repository, we would now be able to inject our own code into Algorithm Search Helper. So that's an example of a directly vulnerable project. Now, the story doesn't end there though, because Algorithm Search Helper is just a library, and we want to see what projects are using this library. So if we take a look at Algorithm Search Helper, we want to see every project that depends on it. So we want to do a reverse dependency analysis search, and this is where that libraries.io data comes in handy. We load it all up into a graph database, and then you can walk through the database and the graph to see what is dependent on this and which projects actually use this, because anything that loads Algorithm Search Helper as a dependency is going to be also impacted by repo jacking. So if we walk through and we see all the different projects, we eventually reach a view instance search. All right, and what uses that? And this is that recursive dependency analysis that we want to do to see what is really impacted by this vulnerability. We reach the view CLI-UI and eventually just the view CLI. So anyone who's familiar with Vue.js will recognize this as the official Vue.js command line tool. And anyone who is developing on Vue.js is going to have this tool installed. So essentially what we have is Algorithm Search Helper as a dependency of Vue, the Vue.js command line tool. So because Algorithm Search Helper, or because that superwolf user renamed their account, now the entire Vue.js ecosystem can be potentially vulnerable to remote code injection. And that really speaks to, one, not only how impactful repo jacking is, but just how impactful in general open source supply chain attacks can be, because one small library can impact huge projects. So that's why it's really important to do this dependency analysis so we can see the full scope of impacted projects. So we start by doing that dependency analysis. At depth 1, those are directly vulnerable projects. And then we move on to depth 2. We've got 32,000 projects, and depth 3, 38,000, 55,000. Eventually, at the depth of 5, we have 70,000 impacted projects. Now, we had to stop at the depth of 5 because as we attempted to compute the depth of 6, it just wouldn't go. And that's because at the depth of 5, we reached some major frameworks that were used by hundreds of thousands of other projects. And it physically took too long for the computer to process the next depth level. And we didn't want to anyways because this was more than enough to prove just how widespread it is, 70,000 impacted projects. And so that's where we stopped the analysis. So now we've got all these findings. Let's actually look at what some of these findings are. So we've got 70,000 affected open source projects. These affect projects in every language, JavaScript, Python, Go. Everyone can load code in from GitHub, and everyone does. And so it's spread up across all these different languages. And it's also spread across all types of projects. We found router firmware, personal projects, websites, crypto wallets, a whole gamut of different projects. And it also affects virtually every single big open source company or open source contributor, such as Google, Facebook, Microsoft, even GitHub themselves were affected. So definitely very widespread. If we actually combine all of the GitHub stars of all the impacted projects, we have 1.5 million GitHub stars, which is a huge amount. And now this last stat is hard to quantify because you can't really tell exactly how much repositories downloaded, and not all project managers would tell you just how many daily downloads it has. But we estimate there's at least a minimum of 2 million daily downloads, unique daily downloads for these impacted projects. So again, a huge number. So have all these projects and they're all loaded up into a graph database. I thought it would be good to make a visualization just to see just how impactful this is. So what I've got here is I'm going to have a little animation, and this blue circle is one project. And the size of the blue circle is scaled up depending on how popular it is. So in this case, this is a project with 1,000 downloads a month. And you're going to see white lines, and those white lines are how different projects relate to each other. So we're going to zoom out here as we look at this one project with 1,000 downloads a month. And at depth level 1, these are the directly vulnerable projects. So you see there's some big projects already that are directly vulnerable. And as you move down, you're going to see the different projects are moving out in circles. So at depth 3, we've got already lots of projects. And you can notice that if we stop at depth 5 here, you notice just how many projects there are and how big they are. That project in the center, you can no longer even see it. And it's overwhelmed by that's the number of projects and the size of some of these projects. And you'll notice at depth 5 over on the right side here, there are some huge projects were impacted, and this is why we couldn't reach depth 6. I think this visualization is helpful to kind of comprehend just how impactful this is. And you can also draw some interesting conclusions and some analysis by looking at this bundling on the left and such, and all these huge projects. So definitely very impactful. Now, remediations, because we need to be able to protect ourselves from repo jacking. So the first and most obvious remediation is don't link directly to GitHub repositories. Always use a package manager. Package managers are there for that. They're meant to be a unique link to a piece of code. So always use the respective package manager, whatever's popular for your language. And even using a package manager, make sure you don't use the package manager, but just link to a GitHub URL, because that defeats the purpose. There's no real safe way to link to a GitHub repository, and it's just easier not to do it. Alternatively, what you can do is something called version pinning. So when a version pinning is usually a package manager will allow you to version pin a dependency, so like a GitHub repository, to a specific commit. So in this case, we see Mailsmith in place. This is that example for the Algola search helper. At the end here, you've got the little hashtag and then a git commit. And so what they're doing is they're version pinning. They're saying, okay, npm only download this specific commit. And this is effective because it stops someone who were to hijack the repository from putting in their own code, since it wouldn't match the right commit hash. Obviously, you don't want to pin to a tag or a branch because those are mutable and those can be changed by the attacker. Now, unfortunately, version pinning is not perfect. As I was doing this research, I also took a look at some of the most common package managers and looked at their version pinning, went through the code, and turns out a lot of them can be bypassed. They're not perfect, and sometimes people are using them just to ensure that they get the right version, and it's not necessarily 100% purely for security. So there are cases where it can be bypassed, and in that case, and that's why version pinning is not the perfect solution. And remediation number 1 is still better, where you just don't link directly to GitHub. There's no way for anyone to hijack a GitHub repository that way. Now, remediation number 3 here, and it's very much like version pinning, are lock files. Lock file is basically a file that ensures that only a specific version of a dependency is downloaded, very much like the version pinning. Now, unfortunately, not all lock files are created equal. Lock files are useful for many other things, security just being one of them. If we take a look at the npm lock file here, over at the top, we've got events, which is a dependency, and this dependency comes directly from the npm index, and it has an integrity check. So that's great, because that way, even if someone were to break into the npm registry and modify that events dependency, that integrity check would fail, and you wouldn't be able to modify that. So that's a great use of a lock file there. Unfortunately, when dependencies are downloaded directly from GitHub URLs, for example, this express, you see it goes to GitHub Vision Media /express, there is no integrity check. It just relies on this git commit hash to be that integrity. And as you saw with version pinning, that can be bypassed in certain cases. So log files are good, again, but not perfect. So the TLDR basically of this talk is that GitHub repositories can be hijacked. You should never link to them directly, and doing so might result in code injection, so just don't do it. Repo jacking, I've written a blog post about it. If you want more information, things I couldn't cover in this talk, repo jacking, explaining the dependency supply chain over at the Security Innovation blog post. Feel free to read that and keep an eye out there for a potential future blog post with some updated findings. You can reach me at any of the common places. And thank you for listening to my talk. I hope you learned something new about repo jacking.
All right, excellent, everyone. Thank you for joining us. This is the Q&A for our session on repo jacking, specifically most of the talk focused on GitHub. But the concept in general is broader, as we've seen recently. In fact, I've seen this kind of vulnerability, goes beyond just repos to some degree, right? As we just recently saw with domain repurposing and the embedded video ads on many popular websites that suddenly found themselves serving up, porn ads on news sites and so forth, right? So I loved the individual advice you gave to folks on how they can protect themselves in GitHub on this. But do you think we can ever get ahead of this kind of thing by just focusing on the individual or even on individual domains? This seems, even something as pervasive and indispensable as GitHub, right? There's a broader problem of trust here that seems like, we're basing trust on identities that are not unique and immutable, as we thought they were, right? And then over time, we see that the improbable becomes almost certain. Do you have any thoughts on like a broader, the broader impact of this in the structure of the industry and how we use and consume resources on the web?
Yeah, that's a great question. A very similar example to repo jacking, which I mentioned in the talk here, was S3 bucket sniping. So the concept is very similar with an S3 bucket, an AWS S3 bucket. You have a unique name, but if you delete a bucket, anyone can re-register it, and any links to the old bucket would now be controlled by whoever re-registered it. So the concept is very similar. As you said, it all links back to the idea of not having a unique ID. Right. So in the case of S3 buckets, they're global, so anyone can register them. So I think the kind of overarching solution to this kind of problem is not necessarily individual, but it's more on the company making these, allowing for that reuse is really the biggest problem here. Solutions are, because obviously, as with GitHub usernames, there's only a certain number. You don't want someone to grab all of them and then there's no more good usernames. So you want to allow some reuse, but you want to have the usernames be more unique. So one potential solution you have there would be have some kind of ID. Maybe like, I know Discord does something similar where you have, maybe GitHub username and then hashtag 37 or whatever unique ID. And that way that specific one can't be reused. And I see that's kind of the solution from the server side there. But yeah, that's just a question, different service need to implement them themselves.
Right. Yeah. And getting everyone to do something like that consistently is always a joy in InfoSec. That's a lot of cats to herd, right?
Absolutely.
So I have a question from a user asking, if they hijack a project, can I see if there's any version specific requests? Like, can I replace a specific version?
Right. Okay. So great question. So there's a couple of different points here. So GitHub hosts Git projects, right? And when you're accessing a Git project, there's many different ways you can do it. So the most common of which is just browse, to GitHub and you arrive to the latest version, right, on the main branch. But you can access projects 3 different ways. So you can access a specific commit, right? And that's like a SHA-1 hash commit of that specific location code, or you can access maybe a branch, right? There could be many different branches, or a tag. So it highly depends on how the project which is reaching this GitHub repository is actually attempting to grab the version. So if it's a branch or a tag, which is very common, maybe you'll tag a certain commit as version 3 or whatever. Unfortunately, GitHub doesn't provide any stats for those. So it won't tell you, hey, this certain branch was downloaded X amount of time, or this tag was downloaded X amount of time. What GitHub does provide is the total number of clones, or the total number of times it's been downloaded, and that includes all the different versions, or the total number of times a specific release has been downloaded. that proves to not be terribly useful because most people don't link to the release files, which are like an individual file that you can host on GitHub. So unfortunately, that I haven't found that to be accessed a lot. A lot of the time, people will be accessing a tag or branch or a specific commit, and in all of those cases, there's no way of knowing. But you can still replace them, and the brute force approach would be replace everything. Go in and if you hijack a repository, you can change all the tags, change all the branches to include whatever you want. Or the more specific approach would be to find a target up the supply chain that you're targeting, see what version they're calling, and then replace only that version.
All right, sorry, we got another question coming in here. I see the typey happening, but it's no, well. There we go. Okay, just general thank you. Okay, great. No, I agree. It was an excellent presentation. The thing that gets me most on this one is just the absolute scale of it, right? Like I knew this was an issue. We've also, like I said, we've seen this in many other kinds of places, but the number of projects, watching that animation go and realizing, like, I want to put out, like, ask somebody to buy you some more servers because I want to see that computation complete out to that sixth level or and beyond, right? It's just mind blowing how interwoven all this stuff is, to the point where you can a relatively small project like that could have that much impact and potential inroads.
Absolutely. I mean, that's the nature of libraries and open source, right? It's all about sharing code, but it also means that everything is interconnected in some way or another. So if you can get one, you can get them all.
And I mean, this is where I was going. Do you have a sense that is this an outlier, or is this pretty? Would you assume that almost any project that has this is in this state would have a similar graph? Right, or is this just like you looked at 100 of these, and this one was the 99th percentile, and the others are like, what's the distribution on?
Yeah, so that graph was actually a graph that included all the projects which were affected. Okay. So that first dot there, that was just kind of like a force scale dot to be like, hey, this is the size of $1,000 a month, but that included everything.
No, thanks for the clarification. I think I was trying to do too many things at once. I missed that. So
yeah, I'm glad you liked the graph, because I'm not gonna lie, it took me quite a while.
Oh no, it's one thing to see the numbers. It's another to watch that animation happen, and it really made it impactful. Mm-hmm. We got one more coming, maybe. Mr. Glass, one of our very own. Oh no, okay. All right. That being said, unless okay, here we go. You showed at the end that not all NPM locks are created equal, but those files tend to be way too large for humans to read, right? So do you know a way to scan for an unlocked include using NPM audit or a similar tool? So
when I was talking about not all lock files being equal, I was referring to lock files being different among different package managers. So in the sense that, NPM does it one way, and then maybe pip does it a different way, and Composer for PHP does it a different way. But if we look at within this specific package manager, so for NPM, effectively, you're right that you can have some dependencies which are in that lock file and some that aren't. I haven't found a way specifically to get a list of those that aren't in that lock file, so I wouldn't be able to help there. But yeah, I guess it would. I'm sure it'd be relatively easy to do. It would be a question of actually doing it. So yeah, unfortunately, I've got no help there.
Given that there isn't an implemented like SBOM out, secure bill of materials, software bill of materials, how can I find out what multi-level dependencies a project has?
That's a great question, and that's actually it's a tough problem, because effectively, you can look at maybe a very specific package manager, and then maybe it has some way of doing it. I know NPM has a way to graph out the tree within NPM, but that often doesn't catch everything. Maybe NPM package manager is only looking at dependencies to the NPM index, so it's not looking at dependencies to a GitHub URL. And with the mass amount of different package managers, it's really hard to have that standardized. And the best I found for that is libraries.io. So I talked to a bit, and that was one of the data sources I used to perform the dependency computation. Libraries.io, it's a website that maintains essentially a database of dependencies. And one of the features they have is if you search up any project, it can be a GitHub repository or any package, really, for basically any package manager, you often have the ability to explore dependencies on the right side there. So if you go there, it'll give you a nice graph, and it might take a little while to compute, but it'll give you a nice graph of the different dependencies a project has. And I found that just to be the best way to see the size, see the scale, and in general, it's a great way to kind of navigate open source projects and their dependencies. So that's what I would recommend.
Great. That's yeah. I mean, even if it's not perfect, you get a 90% picture is give you an idea of the scale of your exposure. Yeah,
exactly.
All right. Well, we greatly appreciate your talk and showing up for the Q&A. This has been a good contribution to the overall discussion here. Thanks for your time.
Thank you very much.
Hope to see you later on.
Absolutely.